Morning to everybody. Dear student, today we are going to start a new topic, that is elimination reaction. You already studied the substitution reaction. Now in elimination reaction is opposite to substitution. In substitution, as you know, the one group gets substituted by the other, that is called as a substitution. While elimination, the groups are removed, or atoms are removed, or a group of atoms are removed from the adjacent carbon atom to form the alkene or alkyne as a product. Therefore, if your starting material is a single bonded, then you will get alkene. If your starting material is a double bonded compound, you will get the alkyne as a product. Now, in E1 and SN1 mechanism, the conditions are same. Therefore, we are getting a mixture of products are obtained in case of the E1 as well as SN1 mechanism. Now, the mechanism point of view, the first step in E1 mechanism is the breaking of the CBr bond to form the carbocation. Therefore, this carbocation formation takes place in first step by breaking of the CX bond. Whenever the group is attached, that means a functional group is attached to carbon, that is called as a C alpha carbon. Therefore, the C alpha carbon means the alpha carbon is there and bond will break. Therefore, this is called as a alpha carbon. Now, next carbon, that is called as a beta, means it is alpha. Therefore, next carbon is a beta carbon, and to this beta carbon, hydrogen is attached. That is called as a beta hydrogen. Therefore, in this case, the first step is loss of breaking of CX bond to give the carbocation. This is the first step. Energy required is high, and therefore this is the slow process, or it is called as a rate determining process. Now, in second step, the base will abstract the beta hydrogen. Therefore, here the beta hydrogen get abstracted, and then loss of beta hydrogen is there, and then it forms a double bonded compound. That means alkene is formed as a product. Now, therefore, here the first step is the halide ion means C-X. X is a halide. This bond breaks to form the carbocation. This is slow step and the first step of the reaction. Now, in second step, this base acts as a nucleophile, and it will, in second step, base will act as a nucleophile. It will extract the beta hydrogen. This will shifted and the double bond will form. Therefore, the double bond will form between C alpha and C beta. There is a alkene as a product. Now, to explain it, or you can understand with the help of three-dimensional view. Therefore, I have taken the three-dimensional view, example of three-dimensional view for the even mechanism. Now here, whenever we are considering the first step, breaking of the C-X bond to form the carbocation. Therefore, I have shown here the carbocation directly. Now, the first step is carbocation formation, then the loss of beta hydrogen takes place. The beta hydrogen abstract this proton. That means the base will abstract beta hydrogen, then this will get shifted and double bond will form. Now here you can see in the picture three-dimensional view, as you know, the p orbitals are there, they are dumbbell shaped. These p orbitals, whenever overlap, above lobes are overlap with each other and below lobes will overlap with each other. Due to overlapping, the pi orbital overlap with each other and they form the pi cloud of electron. Thus, there is a pi bond between this. Now, the pi bond formation takes place, which is shown by these lobes, and therefore, again I will repeat, in even mechanism, the base acts as a nucleophile. Then in step 1, the halide ion leaves forming a carbocation. In second step, the base abstract this beta hydrogen and forming a double bond, that is pi bond, and it gives alkene as a product. Now we are going to study the energy profile diagram. In energy profile diagram, now here in energy profile diagram, it is very clear whenever we are considering energy profile diagram, we have to study the kinetics of the reaction. Also, it is how many step reaction, that each step we have to show the energy also required for that step. If any transition state is there, that we have to show in the diagram. Therefore, energy versus the reaction coordinate whenever we plot it for the even mechanism, then in that case we are getting the first step is there. This is the first step. Here the starting material alkyl halide is there. CX. Okay, this is alkyl halide is a starting reaction. Base is a nucleophile. Then the reaction takes place to form the carbocation, which is an intermediate, and then it gives the product as a alkene. In this case, two steps are there. For two transition steps are there. This is T1 transition state. Suppose, and this is T2 transition. This is T1 first transition step. This is T2 second transition step. Here we have to consider whenever the T1 is there, the energy required for this one transition state, I can draw energy of activation. It should be straight line, curve, okay, arrows are there. Therefore, I have drawn this line which indicate the energy of activation for the first step. Now, this line indicate the energy of activation for the second step, in second transition step. Now, you can compare the energy of activation of the first step will be more high as compared to the second step. Therefore, first step is the slow RDS because energy of activation is high. While second step energy of activation is less as compared to the first step. Therefore, the second step is the fast step. Now, in this first step, E1 and SN1 both are same. In this, the carbocation formation is the first step. That is nothing but the RDS. Therefore, this is the RDS. First step is RDS, where carbocation formation takes place. This is an intermediate which is shown here, carbocation. Now, in second step, this base will abstract the beta hydrogen and it will get shifted. Thus, the new double bond will form between these two carbon. Therefore, suppose this is C alpha bond, this is beta. Therefore, in between two carbons, C alpha and C beta, pi bond formation takes place, double bond formation takes place, and therefore you are getting here the double bonded compound means alkene as a product. Now, whenever kinetic study we are considering, then the rate of reaction depends on some constant into the concentration of the Rx, means substrate. Therefore, rate of reaction depends only on the concentration of substrate. Only one species is involved and hence it is unimolecular reaction. Now the double bonded substitution pattern means how we are getting alkene as a product, whether it is stable or not, that we are going to consider. Now, the more substituted double bond, alkene will be more stable. According to Sedgwick's rule, in all elimination reaction, E1, E2, E1, Cd, more substituted alkene is always obtained as a major product. And therefore, here, you can see here, the ethanol is there, that is a base. It will pick up first carbocation formation as it is even. We are showing in even mechanism. First step is formation of carbocation, and I am showing here the second step directly. The base will abstract this beta hydrogen. This will shift it. It will form the double bond alkene as a product. Now, whatever alkene formed is more substituted. See here, this carbon is maximum substituted, di-substituted, and therefore the more substituted alkene, therefore it is more stable alkene, and therefore more stable alkene is always the major product according to Sedgwick's rule. Therefore, double bond substitution pattern with more substituted double bond, more stable is the alkene, and rate of